So hi everyone, welcome to this course again. So this is the fourth chapter of social network analysis, and today we'll discuss about link analysis. Okay, um, we have already seen that a network consists of two important ingredients. One is called node, other is called link or edge. And while we have already studied different properties of nodes in terms of centralities, right? We have also seen how network grows over time. How do we mimic it using different network growth models? Today we'll discuss different properties of links or edges, right? Particularly, we will look at how social scientist interprets links and how computer scientist models those interpretations using different formulations. Okay, so this chapter, is more about social science kind of perspective, less about computer science perspective, but we'll also define or quantify some of the notions that social scientists has social scientists have already defined. Okay, and at the end of this chapter we will discuss different ways of quantifying the importance of an edge. For example, right, in last case we have defined we have defined different quantifications for nodes. Here we will define different quantifications for edges. Okay, so now this is about link analysis. Next chapter we will discuss a very important concept called link prediction, which is mostly motivated by this chapter. So this is basically the foundation for the link prediction chapter. Okay, all right, so let's get started. So link, as we all know, basically connects two nodes, right? And in graph like social networks, we assume that two nodes are connected by only one link, although there can be multiple links, but we assume that there is no parallel edge. So two nodes are connected by only one link, right? Now, now when we see that a particular link has been formed, right? Now, what are the different philosophies behind forming a link? For example, say you send a friend request to another person on Facebook, for example, right? So why did you do so? I mean, there can be multiple factors. The first factor can be you know that person beforehand, therefore you send the request. Second factor is that you want to build new contacts, new connections, despite the fact that you do not know the person, right? You start exploring new connections and increasing your network, right? Therefore you send a friend request, right? The third factor could be that, okay, you trust the other person, right? Because of this trust factor, you send a friend request. Okay, so there are different philosophies, different ways to form links, and based on that, mostly social scientists came up with multiple hypotheses, right, behind the formation of links. Okay, so if you look at the graphs that we are talking about here, right, in this particular chapter, we will see that we'll talk about normal homogeneous graph where nodes can be of same type, nodes are of same type, edges are of same type. We'll also talk about heterogeneous graph, right, in terms of meta path and all, right, again in the end of the chapter. There we'll see diverse notions of link formation, right? We'll talk about weighted versus unweighted edges. We'll also talk about signed network here, right, where each node, each edge is associated with a sign. Okay, we'll also talk about directed versus undirected edges, right? And we'll also talk about how these edges connect nodes within a certain cluster and across different clusters. Okay, based on this notion of connections within cluster and across cluster, we will define something called weak ties and strong ties. Okay, now if you look at the application of link analysis, why do we care about link analysis? The first and foremost application is entity ranking. Okay, so let's assume that let's assume that in a citation network, for example, right, you want to measure the importance of each citation, right? Now citations, I mean, when one paper cites another paper, right, and say assume that paper X cites 10 other papers, right, it may not be the case that all edges are of equal importance, right? Say for example, your paper is strongly motivated by another paper, so that citation means a lot. The weight of that citation means a lot. Whereas if you look at the other citations, say for example, those citations appear in the background section, or in some other say in the introduction section, right? So those citations are not that important, for example, right? So if you analyze the importance of links in citation network, rank them, weight them appropriately, that will also help you retrieve papers, right, during the search process. Okay, say for example, in Google Scholar search, right, you type certain keyword, maybe that keyword is processed through a citation network. In the citation network, it looks at the search engine looks at the importance of different links, right, and then retrieves documents accordingly. The second application, which we will discuss separately in one of the chapters later, is something called anomaly detection, right, or outlier detection. Generally, anomaly detection, outlier detection are discussed in the context of nodes, right? We try to identify whether a particular node is an anomalous node or not, but it also happens sometimes that we look at suspicious edges, right? Say for example, in case of transaction network, say bank transaction network, right? So these edges, different edges indicate different transactions, right? So the task is to identify fraudulent transactions, right, or anomalous transactions. So therefore these links are very important, right? Third application is mining new patterns. Say for example, the task of link prediction, which we will discuss later. So basically the idea is that how do we predict whether two nodes which are apparently disconnected at a particular time t would be connected or not at time t plus delta t, right? So how can we predict the formation of links? How can we predict the disruptions of links, right, over time, right? It not only helps in say for example future ranking, but also helps in say targeted advertisement. For example, you want to target a specific group of people in a social network or any network to which you want to send your product or advertise your product, right? Now you so basically your task would be to understand, right, the importance of different links with respect to the product or the advertisement that you want to spread. Okay, it also helps in crime prevention, right, and many other applications. So in case of social networks, information spread like hate speech, fake news, you basically the task is to identify edges which are more vulnerable, right, and you may want to protect those edges, right, from being affected by this malicious information, malicious content. It is also important, link analysis is important in an adversarial attack setting, right? So let's assume that you have a network and you want to disrupt the network. Now, what do you mean by disrupting a network? Say, assume that you have a community structure, right, of different communities in a network, and you want to inject, or you want to part of the network, change the network in such a way that the community structure gets disrupted. Now, what do you mean by perturbing a network? Network perturbation can be of different types. For example, you remove certain links, you remove certain nodes. So when you remove a node, its associated links will also be removed, right? You basically remove certain edges, or you add certain edges, or you add certain nodes, right? But this addition or deletion should be very minimum. Okay, so with minimal change, how do we part of the network, right? So that it affects some of the downstream tasks. The downstream task can be, say, node classification or link prediction or say community detection. Okay, so their links play a very important role. These are simple applications, but there are many other applications that we will study in this course. So let's start with a new notion of network called signed network, right? We have discussed in the first lecture that in a signed network we have nodes and edges are associated with signs, right? The signs are generally of two types: positive sign and negative sign. So positive sign indicates that two nodes are friends of each other, right? Whereas negative links indicates that they are enemies, right? So there are many social networks where you can explicitly mark your friends and enemies. For example, opinion /dot, this kind of social networks, you explicitly mark other people as your friends and the remaining people as your enemies, for example, right? Now, depending upon the application, you can also think of another sign, which is a neutral sign, right? Positive sign, negative sign, and neutral sign. The neutral sign indicates that you do not know about that person, but in general we consider these two types of signs, right? Now, certain networks, the signs are explicit, but in other networks signs are not explicit. For example, say, again, let's say citation network, okay? Because this is one of my favorite networks. So in citation network, a link, right, a particular citation, you can criticize a paper. For example, you still cite the paper by criticizing that paper, that okay, this paper is fraudulent, the result is wrong, and so on and so forth, right? So therefore the citation, the link, the sign of the citation would be negative. Okay, and the other signs, when you positively cite another paper, then you can add a positive plus sign. Similarly, say for example on Twitter, right, you follow another person. Now assume that let's consider, say, the account of Donald Trump, right? Donald Trump has many followers, right? Millions of followers. Now it is not the case that all the followers like Donald Trump, right? There are certain followers who do not like Donald Trump, for example. There are followers who like Donald Trump, for example, and there are other followers who are neutral about him, right? So now when when Donald Trump say writes a tweet, right, posts a tweet, his his likers or strong followers, they immediately retweet those tweets, whereas there are other set of followers who just criticize, right, retweet, quote the tweet with some negative sentiment, right? But why they are following Donald Trump, although they are negative about him, but they're still following because they want to keep updated about his activities. Okay, get updated about his activities. So this sign, the notion of sign is very very prominent on social networks, sometimes explicit, sometimes implicit, right? Implicit cases, it might be difficult to figure out. For example, you may need to do some sentiment analysis or understanding whether someone agrees or disagrees, right? Very important application is again e-commerce service. On e-commerce service, you write feedbacks on certain product, right? So this bipartite network, user cross product, when you write a comment about a product, you positively write the review, right? So then the link is positive, otherwise when you criticize it, it is negative, right? Very prominent. So the sign network has been one of the prime focus, particularly in social science community, just to understand how people like, how this trust factor grows over time, and this the formation of trust and distrust, right? How these two factors, right, kind of reinforce each other, and that would further lead to another link, right, in future with certain sign, right? So we'll discuss that depending on the the science of edges, social scientists came up with two different types of theories. One is called a balance theory, and other is called status theory, right? So the notions are different, although the ways we analyze sign network is quite same, but the notions are different. In balance theory, what we look at is that the overall picture, right? We will not look at very micro dynamics. We look at in an undirected graph, for example, right, whether two nodes are friends of each other or not. Whereas in status theory, we look at the fine-grained dynamics to understand whether what's the rationally behind formation of a link. For example, when a particular positive link has been formed, whether the node who has created the link, right? So that node has trusted, or that node has some distrust due to that a positive link or a negative link respectively have been formed. We'll discuss about all these things here. So in balance theory, so this idea was proposed long back 1958-59, where the idea was that let's look at the idea was to understand the balance, right, the social balance in a particular social network or any kind of user network, right, or person network. So now let's focus on a particular type of substructure of a network, which is a triangle, right, a triadic closure, right? So this is a triadic closure, as you see here, a triadic closure, and there are three edges, right? And so how many possibilities are there when we change signs? So so this can be one possibility where all three edges are of are positive edges. This is another possibility where two edges are negative, one is positive. This is another possibility, two edges are negative, one positive, right? And this is another possibility where three edges are negative, right? So let's look at it. Let me draw it. Okay, so this is one possibility where all of them are positive. This is another possibility where negative, positive. This is another possibility that positive, negative. This is another possibility. Can you think of any other possibilities? Three pluses, right? Three minuses, two minuses, two pluses, right? These are the four possibilities. Now I'm not considering the node identity at this moment. I mean, you can say that, okay, if this is A, B, C, right? So AB positive, BC positive. Now if you rotate I mean, if you change the node identities, that would change. But let's just assume that these are the possibilities, right? So we are not considering the IDs for the time being. We are just focusing on the structure, right? So in these four cases, right, let's try to understand from a social science perspective whether these structures, how many of these structures are stable structures, right? Now, what do you mean by stability? We'll discuss. Okay, so let's look at the first structure. Okay, this one. So A, B, and C, right? So A and B are friends, A and C are also friends, and B and C are also friends. So all of them are friends. It's very stable. Stable in the sense like this. I mean, none of these links will break in future. It is less likely because all of them are friends, mutual friends of each other, right? So this is stable. Now let's look at this structure. What it is saying? Say A, B, and C. It is saying that B and C, they are friends and they have a mutual enemy, which is A. B and C are friends and both of them have a mutual enemy, right? A shared enemy, which is A, right? Now this is also stable because this guy is an enemy. So So B and C, who are friends of each other, they would try not to share secret information with A. This is also stable. Okay. Now let's look at this structure. Okay, A, B, and C. This is very important, interesting. So B and C are enemies, but B and C have a mutual friend A. Right? Right? B and C are enemies, but they have a mutual friend A. Now, what do you think? Is it stable or unstable?
Unstable.
Why it is unstable?
Because it will be a problematic situation for A.
Yeah, this would be a very problematic situation for A to maintain. So what would happen eventually is that I mean A would face a problem. Say there is some information. Now A would not be able to understand who to share. Should he share this information to B or C? But B and C are again enemies, right? So what would happen eventually is that A will, right? So this mutual friend A, right? So A will say A would be of under stress, right, to take sides and to support one of the friends, right? And what would happen is that over time, either A would start preferring more to B, right? Therefore, this link will disappear, for example, or A will start preferring C, this will disappear, right? Or A would just leave this friendship totally. Okay. Now, this is an unstable structure, and this is obviously unstable. All of them are enemies, so this edge, all these three edges will vanish anytime. Okay. Now, so intuitively, I hope this is this is understandable. But I mean, how quickly you can remember this? You just you just multiply the sign. So plus times plus is plus, right? Minus times minus is plus, and then plus. So this is plus, and this is plus times minus is minus, and this is also minus. So if the multiplication of signs, I mean, in a very crude way, right, of saying is, if the multiplication of signs is plus, then it's a stable structure. Otherwise, it's an unstable structure. Okay, so so this kind of information is very important. The reason is that whenever you see that there's a structure like this, A, B, and C, and this is plus and this is plus, it is highly likely, according to the balance theory, that another plus edge will be created later. So if you know balance theory well, you would be able to also predict the future link, right, in an appropriate manner, as well as not only the prediction of future link, but also the prediction of the sign of the future link. Okay. So now this is about balance theory. Now let's look at the status theory. So balance theory essentially views the edge sign between two nodes as an indication of the friends or enemy, right? The status theory views the edge sign as an indicator of relative status or prestige, right, of a node with respect to another node. What do I mean by this? So look at this structure here, right? X is connected to Y through a positive link, but this is a directed link. Okay, unlike balance theory where the network was undirected, here the network is directed, and X has created a link from itself to Y. It means that X assumes that Y is more prestigious than X, or Y is more prominent than X. So through this link, you can write that Y is greater than X in terms of prestige. Similarly here, X forms a negative link from X to Y. It means that X believes that X is superior to Z. So X has formed a link from X to Z. So X assumes that X is superior to Z, right? So if you take these two things together, you will see that y greater than x greater than z through transitivity. Okay, but please remember this is x's view, right? Z's view or y's view could also be different, right? So this is all about relative importance or relative prestige, with respect to a certain age, certain node. Okay, but in the balance theory, we have not looked at this relative importance, right? We have basically looked at mutual importance or mutual understanding. So the statement that I'm going to make is very important. What I'm going to say is that balance theory is more likely to overestimate positive links, overestimate stable triangles or stable components than status theory. All right, I will discuss later. What I'm saying is that balance theory overestimates the presence of balanced or stable triangles, right? And underestimate the presence of unbalanced triangle. I will discuss why. Okay, so I'll come to this slide, but before that, let's look at this example. Okay, so let's look at this example. So the question is, we already know that A to B edge is positive and B to C edge is positive. So the task is to determine the sign of this edge. Okay. Now, if you use balance theory will say that this is also positive because this is positive, this is positive, this will also be positive. The first case that I mentioned, right? Now let's look at the status theory. So A thinks that A is superior to B. So B is superior to A. So B greater than A. Here B thinks that C is superior to B. So it means that, right? So if you take the transitivity relation, it means C greater than B greater than A. So that means C is superior to A. Now, if there is a link from C to A, the relation would be negative because C is superior to A, right? Whereas status theory says that this is positive, balance theory says that this is positive, status theory says that this is negative, right? If this is a negative link, right? So positive, negative links meaning that this structure is unstable. Whereas according to balance theory, positive means this structure is stable. So therefore, the statement that I mentioned, that balance theory overestimates the stable triangle, is correct here. Whereas because this kind of structure, balance theory overestimates it as a stable connection, a stable structure, whereas status theory says that no, this is not a stable structure. Okay, so now these are little bit I mean, the differences are a little bit tricky, but when we discuss status theory, the link should always be directed. Okay, when you discuss, now if there's an undirected link, then you consider it as a two-way direction, right? An undirected link is nothing but a direction from this to this and this to this. Okay, now when we discuss status theory, it is very important that we need to take the relative position of relative status. Say, for example, here C thinks that I mean, if these two things, if this condition and this condition satisfied, then the link from C to A would be is expected to be negative, right? but we do not know what is A's opinion, right? We do not know what is A's opinion. So and similarly, when you see that there's a link from A to B, right? B might think that no, I am not superior to A, I am inferior to A. So there can be a link from B to A. So when you look at the formation of edges in status theory, we first need to fix a particular view. Okay, so we assume that okay, at this node, let's fix the view of A, and let's only look at the A's view over its neighbors, right? So if there is a link from B to A, we will not consider this link, because at this point we only consider those links coming out of A. We consider this link or say this link, for example, right? When we come here, right, we will not consider this link because this has already been exhausted, but we'll consider this link, right? So at every node, we need to fix someone's view, and accordingly we need to form the edges. Okay, in case of status theory. All right, so let's go back a little bit. So in status theory, the two metrics are very important. One is called generative baseline, and the other is called the receptive baseline. What is generative baseline? Generative baseline of a node is the fraction of positive signs generated by a node. Okay, now let's look at A. Okay, and A has this link, right? So how many links A has generated? Only this link A has generated, because other three links are not generated by A. Other three links are incoming links. They are generated by some other nodes. So how many nodes? How many links A has generated? A has generated only one link, and out of this one link, how many of them are positive? One, right? So generative baseline of A is 1. Let's look at B. The generative baseline of B is 0, because B has generated 2 links and both these links are negative. So 0 by 2, right? Similarly for C. What is receptive baseline is the other way around, right? Number of edges, number of incoming edges, and how many of them are positive. So in case of A, there are 1, 2, 3 incoming edges, and out of them 2 are positive. So this is 2 by 3, right? For C, this is 1, 2, and 3 incoming edges, and all of them are negative. So this is 0 by 3, right? So this generative baselines and receptive baselines are useful to understand the overall status of a particular node. Say, for example, if the generative baseline is much higher than the receptive baseline of a particular, can you hear me, guys? If a generative baseline is if a generative baseline of a node is higher than the receptive base, much higher than the receptive baselines of the node, what does it indicate? It indicates that generative baseline is higher. That means the node feels that that the node is inferior to most of the nodes, which are the neighbors of the particular, because generative baseline is high. That means the node has produced a lot of positive links, right? Where the receptive baseline is lower, meaning that other nodes, other neighbors also think that this guy is inferior, right? So if there is a balance between generative baseline and receptive baseline, then you think that okay, this guy is of this guy has a reasonable position. Whereas if the generative baseline is much higher and receptive baseline is lower, it means that this guy this guy also thinks that he's an inferior guy, and other nodes also think that so he is an inferior guy. Whereas if the receptive baseline is very high, generative baseline is low, right, less, then it means that the other guys also think that he is superior, and he also thinks that he is superior. Okay, very interesting concept. if you read more and more papers in social science, you would get to know more about different experiments that were conducted to study this kind of network. But for this particular course, I think this is good enough. Now let's move to the next concept, which is the ties or links between persons. Okay, so these interpersonal ties or interpersonal links are very important, and depending upon the strength of the link, you can have 3 different types of links. One is called a strong link, other is called a weak link, another is called the absent of a link. Absent of a link means there is no edge, there is no link at all, right? Now let's look at very carefully what's the meaning of a strong link and a weak link. So so let's assume that you are a part of a company. Okay, say you are part of a TCS. Okay, and you have few friends who work in IBM, you have few friends who work in Infosys, but you are strongly a part of TCS. So most of your friends belong to TCS, close acquaintances belong to TCS, whereas you have some friends who are not that close, but they're still their friend, still your friend. They belong to IBM or Infosys, right? Now, so therefore, the connections, the ties within the TCS, TCS community, TCS group are strong ties because they are your close friends. Whereas the ties from you to other friends in different other industries, IBM and Infosys, those are weak ties, right? Weak ties in the sense like, say, for example, you call them once per week or twice per month, whereas you talk to your internal friends within TCS a lot, right? Quite frequently. So if you just look at, the user interaction, you will see that the age weight within the close group, right? The weight of the ages within a closed group is high, much higher than the age weight across different clusters. So, right, so you have strong ties within a cluster, you have weak ties across clusters. Now let's assume that you want to switch your job, you want to move to other company, right? So what do you think, which kind of friends, the close friends, the friends which are connected by strong ties, or the friends which are connected by weak ties would help you a lot, right, for this movement? So your weak ties will help you a lot because your strong ties would never let you, right, move from TCS to IBM, for example, right? So your strong ties, your close friends, they would not tell you any opportunities which may have arisen in the other industries, whereas your weak ties from other industries, they would help you move from TCS to other company, for example, right? Now there was a very interesting experiment happened in 1973 by Granovetter. Now he's a very famous social scientist, and he exactly did this experiment in 1973. So he focused on a particular group of people who had recently changed during that time, changed the company, their jobs, and he called all those persons and asked who helped those guys to move from their old job to the new job, right? And it turned out that most of them said that their weak ties, right, those are not close friends, might be acquaintances but not that close friend, they help them a lot to get a good job, right? So now the interpretation of strong ties and weak ties, not only in this context, but also they have other significance in other contexts. For example, say you right? So say for example, you want to you want to break a network, right? You want to break a network so that your number of communities or number of connected components in a network starts increasing, right? So what do? You target weak ties and you start breaking those weak ties, right? Because these weak ties, these weak links are nothing but those links which connect components or which connect subgraphs of a graph, right? Subgraphs which are not that well connected. So let's assume that this is a subgraph and this is also another subgraph, right? You see a connection like this, you see another connection like this. So you start to, in order to break the network, you start attacking this edge and this edge. Therefore, the number of components will also increase. Okay, so it has a lot of implications in social network, in any other network. But how do we quantify a strength of a tie? Because it is all about strong and weak, right? Strong versus weak. Now, how do we measure that a particular link is a strong link and another link is weak link? Okay, so the simple measurement is that you look at the neighborhood intersection of the two endpoints of a link. Okay, so this gamma x indicates the neighborhood of x. Now say this is x and this is y, right? This is neighborhood of y. So this is essentially a Jaccard coefficient, right? So in this case, so x has a, b, c, d, right? So gamma of x is okay, e, f, right? Is a, b, e, and y, right? Gamma of y is c, d, f, and x, right? So if you do the intersection would be only what would be intersection? Intersection would be 0. Right? And union would be what? The size of the union of this one would be 1, 2, 3, 4, 5, 6, 7, 8. So the less, so the more the value of this neighborhood intersection, the more the value of the neighborhood intersection, the strong the link is, right? The stronger the link is. The more the value of the neighborhood intersection of two endpoints, the stronger the link is. The less the value, the weaker the link. Okay, simple. It's a very simple way of looking at it. You can also measure it in different ways. For example, you can say that okay, the strength of a link can be indicated by the number of components that would be formed if you remove that link. The number of components that would be formed if we remove that link, right? This can be another way of defining the strength. There can be another way of defining the strength. Okay, you can say that okay, because after cutting a particular link, two different components are generated. This is a very strong assumption. Okay, let's make it a little bit easy. Okay, let's make it a little bit loose. Okay, so what you are saying is that okay, the strength of a particular link is determined by the reduction of shortest path distance from x to y after removing this link. Okay, so let's assume that there is another edge like this. Okay, so let's assume, let me write it, draw it afresh. Okay, and Okay. Okay, let's assume these two structures. Okay. Now I'm interested in understanding the strength of this edge, right? So what I'm saying is that the strength of this edge is determined by the change in shortest path distance from x to y after removing this edge, right? So what's the shortest path distance from x to y is 1, both the cases 1. Okay, now if we remove this link, the shortest path distance from x to y would be 1, 2, 3, right? So 3 minus 1. In this case, if you remove the link, the shortest path would be 2, right? So it means that this link is a weak link, okay, and this link is a strong link, because after removing this edge, the shortest path doesn't change much, whereas after removing this edge, the shortest path changes a lot. Okay, this is another way of looking at it. Okay, so depending upon the notion, depending upon the application, you define in different ways. Right. So now triadic closure, we have already discussed what is triadic closure in the first class when we discussed about clustering coefficient. I hope you remember this, right? But here we, again discuss it in a different manner, more of a social science perspective, that why a particular link has been formed. Okay. Now, triadic closure says that at time, t minus delta t, A and B are connected and A and C are connected. At time t, you see that okay, there's some chance that B and C would be connected, and at t plus delta t, B and C are connected. Okay. Now, what is the reason behind formation of a link from B to C? Okay, so there can be three different reasons. The first reason is the opportunity. Now, what do you mean by this? So it means that every mutual friend. So A is the mutual friend of B and C. So every mutual friend gives them. So A has given B and C some opportunity to meet and to become acquainted with each other, to become friends of each other, thereby increasing the chance of developing a connection. Right now, this kind of things happen quite frequently. For example, say for example, let's take any incentivized structure, right? Say for example, in Big Basket. Okay, let's take an example just for the sake of taking. So in Big Basket, what they offers is that if you share some the link first time to some of your friends who have not opted for Big Basket services so far, and if your reference leads to a new customer, right, of Big Basket, you will be rewarded. So this is nothing but what? This is nothing but creating an opportunity, right? So let's assume in this particular case that there are three entities. One is Big Basket, other is your friend, and other is you, right? So you are a mutual friend of your friend and Big Basket, right? But Big Basket and your friend, they are not connected, right? Now, because that you have an opportunity, right? You also have an incentive, right? That if you connect them together, you will get some reward. Therefore, you'll force them to become friends of each other, right? So this comes under opportunity. This also comes under incentive. Okay. Trust. What is trust? Why trust is a factor here? If in a network, right? So let's assume that that connections are established only based on trust. There is no other factor. Only based on trust, the connections are established. So we have already seen in case of balance theory that if this is these two edges are positive, that means B and A they trust each other. Also, A and C trust each other. Now, due to the stable connections that we discussed in balance theory, it is highly likely that B would start trusting C, right? So this age would also be formed. So there's a very interesting theory. It's called strong triadic closure property. Strong triadic closure property. Strong triadic closure property, right? It says that if two nodes have a mutual friend, if two nodes, let's assume that they are not connected, if two nodes have a mutual friend, right, at time t plus delta t, at least a weak connection will be created, if not the strong one. Okay, if B and C have a mutual friend and B and C are strongly connected with A, right, this is plus, strongly plus, what would happen at t plus delta t is that at least a weak connection will be formed between B and C, if not the strong connection. Okay, all right. So, and we know how to measure the triadic closure. We measure the triadic closure using clustering coefficient, right? The total number of edges among the neighbors and how many edges are actual there. So possible number of edges among the neighbors and how many of them actually exist, okay, in real world. So see an example here. There is another important concept which is called Dunbar number. Okay, what is Dunbar number? Now, Dunbar number, the term was coined by famous anthropologist Robin Dunbar. So he, you know, what he tried to understand, he tried to understand the cognitive limit of a person, right, to remember his acquaintances, his friends, right? Say, for example, I have 3,000 friends on Facebook, right? It is not possible for me to remember all 3,000 friends, right? Some of them are close to me, very close to me. Some of them are not that close to me. Some of them are very far from me, but still they are friends, right? So in cognitive study, it directly supports the strong and weak ties, right, in real world, right? So what Dunbar did, Dunbar tried to understand that at a particular time, how many friends you can remember. Okay, and it turned out that the number ranges between 100 to 250, with the average cognitive limit is 150. That means at a particular point you can remember at most 150 friends, right? You may have 3,000, 4,000 friends, but you would not be able to remember each of them. So based on that, he encircled your friends into different groups. So this is you, right? This is you. This first circle, so this is your very strong ties, right? Second circle, little bit weak, right? And he mentioned that if you take the innermost circle and the next circle, that would encompass 150 friends very easily. Okay, so he kept on grouping nodes into different circles, and turned out that you can go up to 10 such circles, right? Whereas first two and three circles, the innermost 2 and 3 circles are the constitute the nodes or friends which you remember, and that also correlates with human brain size. Okay, that was also shown in that experiment. So as if what he tried to say is that in this 150 nodes, are close to you and they form strong ties, whereas other nodes are not that close and they form weak ties. Okay, so all these concepts are interrelated. Right. So this we have already discussed, but let's discuss it very briefly here. The concept of bridge and local bridge. Okay, bridge. Now remember, I mentioned that there are lots of implications of strong ties and weak ties. One of this is bridge. Okay, so bridge is an edge or a tie which after removal disconnects the network, right? Meaning that number of connected components will increase. Okay, as you see here in this particular case, if you remove this red line, you see that there are two components emerging and they are not connected, right? And as I mentioned earlier, this is a little bit a strict definition. So what you do is that instead of looking at the components that are being formed, you look at the distance. Okay, you look at the distance that would if you look at the distance between x and y are two endpoints of a particular edge, and after removal you look at the shortest path. Okay, for example, in this case here you see that A and B, right, they are connected, and you want to understand whether this is a local bridge or not. You disconnect it. Once you disconnect it, you look at the shortest path length, right? This is 1 2 3 4. It would increase a lot. So local bridges are ties between two nodes in a social graph that are the shortest the shortest route by which information might travel from those connected to one end to another connection would basically increase, right? So on removal of the local bridge, the distance between these two nodes will be increased to a value strictly more than 2. Why strictly more than 2? So strictly more than 2, meaning that let's assume that there is a connection like this. Okay, if you break this connection, okay, now the distance between A and B is 1 and 2, right? So this is the threshold. Okay, if this kind of connection exists, what does it mean? This kind of connection exists, that means that before removing a particular edge there was a triangle, right? So if a node is a part of a triangle, then that if an edge is a part of a triangle, then that edge cannot be a local bridge. Okay, so but let's assume that there is a connection like this, and this connection doesn't exist. Okay, this connection doesn't exist. Okay, so then if you remove this, the distance would be 1 2 and 3. Now this is allowed. So the distance would be more than 2 if you remove the particular edge, right? Which also guarantees that that edge was not a part of any triangle before. Okay, now this is the concept of local bridge. This is a little bit loose definition compared to a bridge. Okay, so and how do we measure this? Again, the measurement is very easy. You measure this by look at the neighbors, right? So let's say again in this particular graph, right, I'm not drawing the interstructure. Let's assume that this is there, this is there, okay, this is there, this is A and B, right, this is there, this is there, right, okay, like this. Okay, so in this particular case, A and B do not share any mutual neighbors, whereas if there was a edge like this, then A and B share a mutual neighbor here, right? So you look at the mutual neighbors of A and B. If there is no mutual neighbor, then A and B are this particular edge is a local bridge. But if there's a mutual neighbor, intersection is at least 1, that means it would not be a local bridge. Okay, So this is called edge embeddedness. Edge embeddedness is nothing but the neighborhood intersection of X and Y. Okay, if it is 0, that means it's a local bridge, right? Otherwise not. So the importance of local bridge, we already mentioned this close. So this local bridges are nothing but weak ties, right? Information close friends receive overlap considerably, right? People receive more novel information through acquaintances than from close friends. So if you want to get more, new information, for example, again, let's take a scientific discussion, okay? And you are discussing with your lab mates, right? Who are close, versus sometimes you also discuss, your friend who say study in US, right? So it is highly likely that you would get new information, novel information from your friend who is not part of your institute, right? Is part of some other institute, right? So weak ties act as a bridge and help a person gain access to newer and wider information. In case of stress and conflict between two groups, weak ties act as a mediator, right? And this is also, this is very understandable, because let's assume that you are part of a group, a strong group, and there are two nodes in the group who are who have very conflicting nature, right? And let's assume that those two nodes are also connected to a mutual node who are who is their acquaintances, not a strong friend, right? So that guy would help possibly resolve the conflict. Okay. Removing local bridges can lead to the formation of echo chambers. Now this is very important. What is echo chamber? Now echo chamber in social science, again in social network, echo chamber is basically a community, a group of nodes who echo each other's, a group of nodes, a group of users who echo each other's opinion, right? For example, let's assume that there's a group and the group supports Democrats, right? And so whenever somebody says something positive about Democrats, all the other persons in the group would retweet that tweet, for example, or share the posts, right? And basically within a chamber, users echo each other's opinion, right? Now echo chambers, in certain definitions, echo chambers are nothing but communities in a network. Okay, these communities are opinion oriented communities. These communities may not be dense, right? But they have very similar opinion, homogeneous opinion. That's why they form a closed group. So what happens is that this local bridge connects these two echo chambers, so multiple echo chambers. When you cut the bridge, echo chambers become much more prominent. Okay, so let's assume that there are two communities, Democrat community and Republic community, and there's an edge between Democrat and Republic. So that edge is a dangerous edge, because that edge would essentially transfer information from one community to another community. So when you cut the link, these echo chambers would become even more stronger, right? So in case of disease outbreak, right, these local bridges may cause the disease to transmit from one group to another. This is very important. So therefore your task would be to somehow vaccinate this edge, meaning somehow vaccinate these two nodes, two endpoints, so that the disease will not spread from one community to another community. Okay.